Duck typing is one of those ideas that sounds strange at first, but once it clicks, it changes how you think about types entirely. Here is a question: you have a function that takes an object and calls .quack on it. Should you care whether that object is a duck, a person, or a rubber toy as long as it has a quack method? In statically typed languages, the compiler says yes, you must care. In dynamically typed languages, Python, Ruby, JavaScript, the answer is no. If it quacks like a duck, treat it like a duck. That idea has a name: duck typing. Duck typing comes from the duck test, attributed to the poet James Whitcomb Riley in the 1880s. If it walks like a duck and quacks like a duck, then it is a duck. In programming, the equivalent is, if an object has the methods or attributes your code needs, you can use it regardless of what class it actually belongs to. No explicit interface declaration. No inheritance hierarchy, just the presence of the right behavior. In a statically typed language like Java, a function that accepts a duck must receive something that is declared as a duck, or at least implements a duck interface. The type checker enforces this at compile time before any code runs. In Python, there is no such check. You call .quack, and if the method exists, it works. If it does not, you get an attribute error at runtime. The type system trusts you to pass the right thing and finds out immediately if you did not. Here is a real Python example. Suppose you write a function called makeItQuack that calls .quack on whatever you pass in. A duck class has a quack method. A person class also has a quack method. A RubberDuck class has one too. All three work. None of them need to inherit from a shared base class. None of them need to register against an interface. The function just calls the method and Python finds it. That is duck typing in practice. Duck typing is powerful, but it shifts the burden of correctness. In a statically typed system, the compiler catches type mismatches before deployment. With duck typing, you find out at runtime, potentially in production. The standard mitigations are unit tests that exercise each type you expect, clear documentation of the expected protocol, and in modern Python, type hints with tools like mypy that let you opt into static analysis without giving up duck typing's flexibility. Python formalized duck typing's implicit idea into something explicit with abstract base classes, introduced in Python 2.6. An ABC lets you define a protocol, a named set of methods an object must implement without forcing inheritance. The collections.abc module ships ABCs for common protocols, iterable callable mapping sequence. You can register existing classes against them, or let Python infer conformance through structural subtyping. It is duck typing with an optional contract. Duck typing shows up everywhere in Python's standard library. The built-in len function works on any object that implements dunderlen. The for loop works on any object that implements dunderwriter. The plus operator works on any object with dunderadd. These are implicit protocols, not declared anywhere, just expected to be present. When you write a class that implements dunderlen, you are opting into a protocol that len and the rest of the language already know about. That is the real power. The language's own machinery is built on duck typing. Duck typing versus static typing is not a binary choice anymore. Python's type hint system, introduced in 3.5, lets you annotate variables and function signatures without enforcing them at runtime. Tools like mypy and pyrate run static analysis against those annotations, catching type errors before execution. The protocol class in the typing module lets you define structural interfaces, exactly like ABCs but lighter, that describe what an object must support without naming a concrete class. You get the flexibility of duck typing and the tooling of static analysis. Most production Python code today uses both. Thanks for watching.